All right, everybody, welcome to Math with Grace. Today we're going to be going through Pre-Calculus, Unit 3, Sections 1 and 2. Section 1 begins on page 5, and it's titled Solving a Right Triangle. And we are going to begin with the lengths of the sides, okay? It starts off here by asking us the question, what is trigonometry? And then answering the question. It says it's a branch of geometry that deals with triangle measurements. Throughout history, trigonometry has been used and evolved from the need or desire to measure what cannot physically be measured. Okay? They used to use it in measuring the distance to the stars. Okay? Bottom of the page, right triangles. So we're going to review some things about right triangles you should already be familiar with. A right triangle has one 90-degree angle and two acute angles. The sum of the measure of the two acute angles in a right triangle is 90 degrees. The longest side of a right triangle is called the hypotenuse. The two shorter sides of a right triangle are called the legs. The Pythagorean theorem applies only to right triangles, where A and B are the legs and C is the hypotenuse. Trigonometric ratios express relationships between the sides of a right triangle. Let's turn the page. Top here of page 6, we have the hypotenuse, which is always across from or opposite of the 90-degree angle, and it's also the longest side of a right triangle. If we're talking about angle A, the side adjacent to angle A is the side that helps make angle A. The hypotenuse is always going to be one side, but the other side that makes angle A is the one adjacent to angle A, and therefore the one opposite angle A is called the opposite. Okay? If we were to switch it to angle B, then this would be the adjacent side and this would be the opposite side. Okay, so we have to remember our opposites and our adjacents, and that's what this next column talks about. Trigonometric ratios, once they are established for a certain angle, exist no matter how big the triangle is. And so we can use sine, cosine, and tangent to help solve for the different sides. The sine of angle A is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. Some of you may recall learning SOHCAHTOA, right? Sine opposite hypotenuse, cosine adjacent over hypotenuse, tangent equals the opposite over adjacent, SOHCAHTOA, right? And then in this little box, it has some other sayings, I guess, that memory strategies. I'm not going to go through them. If you need one, then please go right ahead. But SOHCAHTOA is usually what we use. Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. Looking at some of these examples. Find the value of the sine of P. Well, P is going to be the angle that we're working with. So the sine of P is going to be opposite over hypotenuse. Remember, the hypotenuse is opposite of the right angle. If you need to mark these things, this would be the opposite, this would be the adjacent, and this would be the hypotenuse, right? So opposite over hypotenuse is 3 over 5. For this next example, it says find the trig values for Q. So they want all of them. Opposite is over here, adjacent is here, and the hypotenuse is here. So for the sine, we have opposite over hypotenuse, so 4/5. For the cosine is adjacent over hypotenuse, or 3/5. And for the tangent, it's opposite over adjacent, or 4 over 3. Okay? Now, the example at the second column on page 7, they want you to find the value of the tangent of F. Okay? Here's my angle F. This is the opposite, this is the adjacent, and this is the hypotenuse. Now, to find the tangent, we need opposite over adjacent, but they didn't give us the length of the adjacent side. But because it is a right triangle, we can use the Pythagorean theorem to solve for the adjacent side, which they did here. Do not make this a fraction, just leave it as a radical. But once we have that radical, we can say that our tangent is going to be 2 over the square root of 5. But remember, in math, we cannot have a square root in the denominator, so they work it out, and the answer is 2 times the square root of 5 over 5. All right, one more example on this page. If the sine of angle A is 5 over 13, find the cosine of angle A. Well, this tells us the parts, right, of this triangle. And if it helps you to draw it out, what a scraggly thing, right? We know the sine of angle A is 5 over 13, okay? You would have to use the Pythagorean theorem to solve here. Consequently, 5, 12, 13 is what they call like a golden triangle, because all the numbers end up being whole numbers. But using the Pythagorean theorem, they found that the missing side was 12, but what they're asking for is the cosine, which then would be 12 over 13. All right, let's turn the page. Now, most of page 8 is all about using a calculator to solve for the answers for these problems, because most of the trigonometric values are irrational numbers. And so I'm not going to go through all they have to say about calculators and whatnot. If you have a special type of scientific calculator, I would consult the instruction manual. I'm sure it can be found online fairly easily, and figure out how to use your calculator that way. I'm going to show you on this calculator. I can also show you on this calculator. If you have something more advanced, again, you're going to have to look it up, or perhaps it's even just similar to what we're doing here. So for this example on page 8, they want us to turn that one on too. They want us to find 2 basically times the sine of 30 degrees. Now on my calculator, when I hit sine, it comes up with the little parentheses, right? In this example they're showing, they say you have to put the number in first and then hit the button. That's how it would be if I was doing it on my phone, okay? Because there is a scientific, to some extent, functions on my phone. So that's what I would have to do on my phone. But on my calculator, I'm going to put in the sine of 30. I'm going to close my parentheses, and then I'm going to hit times 2, okay? And I'm pretty sure this is the same over here. So sine of 30, close my parentheses, times 2. So these two calculators are the same. So I'm going to set this one aside, and we get 1, okay? And it wants you to check these values with your calculator to make sure your calculator is in the right mode, because there are a lot of different modes on these scientific calculators. Mine are listed kind of translucently at the top, and then the modes that I'm in are highlighted. So do take the moment to check your calculator with these results to make sure your calculator is in the correct mode. This next example, they want you to evaluate the cosine of 60 degrees times the sine of 30 degrees. Same thing, cosine 60 degrees times the sine of 30 degrees. Now those two things are the same, and we'll talk about them in a moment. And you hit equals, and you get 0.25, which is the correct answer, okay? So when they're asking you to do problems like this, for this example here, tangent of the quantity 20 plus 30, just add them together first and then find the tangent. The cosine of 45 degrees divided by 5, okay, just like we've been doing. Make sure you close your parentheses, all right? It's always important to close your parentheses. Now, continuing on here, it says, knowing that the ratios between the sides of a right triangle remain constant, allow you to determine measures without actually measuring. That's the whole point of these trigonometric functions. The trig functions allow you to find the lengths of sides in a right triangle given only an acute angle and one side. So that example is up here. It says, for the triangle shown, find the values of x and y. So we have a right triangle with a 35-degree acute angle. We already can figure out the measure of this angle because there's only 180 degrees inside of a triangle, right? Here's 90, here's 35, so we could figure that out. They're not really asking that, but we could if we wanted to complete this triangle. Now, the opposite is the x, the adjacent is the y, and, or sorry, no, it's not, is the 7, sorry, and the y is the hypotenuse. So to find the sine, we would have to find opposite over hypotenuse, neither of those things that we have. So that is not something we want to start with. But to find the adjacent, we do the cosine, we can do adjacent over hypotenuse, and that one we can actually solve because we can put in our calculator cosine of 35, right? And then solve this problem, which is what they've done here. They multiplied both sides by y to get y out of the denominator, and then they divided both sides by cosine of 35. So y, which is the hypotenuse, is equal to 7 divided by the cosine of 35 degrees. And so the answer is 8.5. You're going to have to round on most of these because, remember, trigonometric functions are mostly irrational numbers, and so there's a lot of decimals. Usually we round to the 10th place. Okay? All right, let's turn the page. Don't forget the review section up at the top, but let's take a look at problem number 1.5 through 1.7. It says, match the following items, label the triangle using angle B. Okay? The triangles are not always drawn to scale, of course, and that's fine. So what is the hypotenuse of angle B? Remember, the hypotenuse is always opposite the right angle, and it's always the longest. And since we know all the sides, we know which side is the longest, and that is the 13, or C, right? And so then what about B? What is the opposite side of B? Well, opposite B is 12, so that's B. And the adjacent side, remember, is the side that creates B, and that's a 5. All right? Over here on page 11, problem number 8. Complete the following activities. The triangles are not drawn to scale. Evaluate sine of A for the triangle shown. Okay, here's A. They want us to evaluate the sine of A. And remember, the sine is opposite over hypotenuse. But they didn't give us the hypotenuse, so we need to solve using the Pythagorean theorem. And that tells us that 6 squared plus 8 squared is going to equal C squared. 6 squared is 64. Oh, it's not. 6 squared is 36. 8 squared is 64. And this is equal to 100. Another golden triangle. So C is equal to 10, right? We take the square root. Now we know that the hypotenuse is equal to 10. We can solve for the sine of angle A, which is opposite over hypotenuse, or 6 over 10, which is basically 0.6, 6/10, which is letter A. Okay? Sometimes we're going to have to solve for an extra piece. Right triangle ACB has side lengths of C, which is equal to 17 inches, and A, which is equal to 8 inches. Okay? Solve for the exact length of side B. Now, hopefully what you've noticed, or what you should notice, the angles are always capital, and the sides opposite them, when written like this, are always lowercase. So this side is opposite this angle. Angle A is capitalized, side A is little. Angle C is capitalized, side C is small. Capital B, small b. So we want the side opposite angle B, which is the small b, right? We have 2 of the sides. To solve this, we need to use the Pythagorean theorem again, because A squared, or 8 squared, plus B squared is equal to C squared, okay? 8 squared is 64. Oh, 17 squared, let's see here, is 289. Subtracting 64 from both sides, we get 225. Taking the square root of that, close your parentheses when you're doing this, and B is equal to 15. Okay, so B is equal to 15. Since both of these were inches, we're dealing with inches, so letter C. Okay, do a couple more. We'll do one more of these and then we'll come down here to number 14. Round to 4 decimal places the tangent of 75 degrees. I want this to be seeable here. So if we want the tangent of 75 degrees, close our parentheses, it's going to be 3.73205. They want 4 decimals. So 3.732. I'm rounding that 0 based on a 5, so it's going to become a 1. All right. Remember, when you're looking at like this number 11, picture these parentheses there so you don't get confused on what exactly the process that's happening. Looking at number 14. In triangle MPN, P is a right angle. If the cosine of n is 3/5, which of the following statements is true? Okay. I like to draw out things when they don't give me a drawing, right? They're saying P is the right angle, which is here. So I'm going to say this is MPN. All right. If the cosine of n is 3/5, remember cosine is adjacent over hypotenuse, which of the following statements are true? That the sine of m is 5/3? Well, no, the sine of m would be 3/5. Not 5/4. We don't even have a 4. We don't have a 4. 3/5. The sine is opposite over hypotenuse, so it's letter D. Okay? Go ahead and finish the rest of these problems and meet me back here for the next part of this section. The next part starts on page 13, and it's about angle measures. Okay? Direct angle measures, it says, angles are commonly measured using units of degrees, where 1 degree is 1/360th of a circle. Okay, we're talking about a circle, 360 degrees, and so we talk about degrees as one piece of that. The degree is broken down into 60 smaller units called minutes, and each minute is broken into 60 smaller units called seconds. The expression 30 degrees, 10 minutes, 15 seconds is read just as I just read it, okay? Where 60 minutes, so the single tick mark is a minute, double tick mark is a second. 60 minutes equals 1 degree. 60 seconds equals 1 minute. 3,600 seconds equal 1 degree. And then here are some conversion ratios, right? 60 minutes is 1 degree, or 1 degree is 60 minutes. 60 seconds is 1 minute, or 1 minute is 60 seconds. And then 1 degree is 3,600 seconds. So here's an example of how we're going to be using these. Convert 30 degrees, 10 minutes, 15 seconds to the decimal degree form. So basically, the 30 degree is the only thing that's going to be a whole number, because minutes and seconds are all parts of that. So to figure out how many decimal point minutes and seconds we have, we leave our 30 degree as a whole number. We take our 10 minutes, and we're going to basically divide it by minutes, because we have 0.166 of a degree. And then we take our 15 seconds and we divide that by 3,600 to get this, and then we add them all together, and this is the answer to this measurement, but in decimal. Now, these measurements are often used on boats, and surveyors use these types of measurements. Okay, a lot of times on ships, they use these types of measurements. Okay, let's turn the page. Now, at the top of page 14, they have another example. Convert 30 degrees, or 30.1708 degrees to minutes and seconds. Okay, and then they go through the process. We are going to leave the 30 degrees on their own, and we're going to start with the 0.1708, multiplying that by 60 minutes, okay? And we get 10 minutes, 0.248. The 0.248 are the seconds that are left over. So we take that and we times it by 60 seconds. And we get 14.88, which they've rounded up to 15. So 30 degrees, 10 minutes, 15 seconds. Now there's a note here. That says a lot of calculators, scientific calculators, are made to or have the functionality to process these types of problems. And I'm going to show you how to do that on my calculator. There's this button here that has a little open circle, a degree, and then 1 comma, and then 2 commas, okay, the minute and the seconds. So if I put in 30.1708 and I hit degrees, okay, and then equals, it tells me it's 30 degrees, 10 minutes, 14.88. So they rounded it up to 15 seconds. Okay, let me look at this other calculator and see if it has a similar function. Let's see here. Oh, yeah, right here. Degrees, minutes, seconds. Okay, so most likely your calculator does too, so I would check that out. Okay, moving forward. It says here that each angle has exactly one trig function value. For every angle, there's one value that corresponds to that angle. And so we have to use the inverse sine, cosine, tangent function to figure that out. So it says find the angle to the nearest degree whose cosine is 0.3746. Now, a lot of books used to have, and this one might have way at the back, tables. Okay, I don't see it referencing a table, but they used to have tables. That's how they did it before calculators were so easily to come by. They made tables and it had all the measurements in it. You would just have to like go and search for it. Now that calculators are so easy and available, we can just do it on our calculator. So the cosine, so we want the inverse. And so my inverse cosine is right underneath my cosine button. So I'm going to hit shift cosine. So it's cosine the inverse, right, to the -1. And then I'm going to put in 0.3746, closing my parentheses, and hit equal. And it's telling me it's 68.00000. So basically 68 degrees is the angle whose cosine is 0.3746, okay? We'll do one more. Evaluate the inverse cosine of 0.1717. Okay, close your parentheses. 80.11 or 80 degrees. All right. Looking at another example here at the top of page 15, they want you to evaluate the inverse tangent of the square root of 3. Again, not too challenging. Is something we can put into our calculator. We're going to take the inverse tangent and we're going to take the square root of 3. Make sure you close both sets of parentheses, right? This square root of 3 had a parenthesis and this outside of the radical had a parenthesis. And it tells me that's 60 degrees, okay? So calculator work is going to be vital. If you need a calculator, please let me know and I can see what I can do. Just as with side lengths, angles in triangles can be measured indirectly by using trigonometric ratios. Here's an example. In triangle ABC, C is 90 degrees, A is 3, I like to write it in, and C is 5. Find the measure of angle B to the nearest degree. Now, if we're looking for angle B, we are looking for the cosine of angle B, right? Because the numbers we have related to angle B are the cosine numbers. 3, the adjacent, and the hypotenuse, 3 over 5, okay? 3 divided by 5 is 0.6. And now we can use the inverse of B, the inverse cosine, sorry, of 0.6 is going to give me the angle measurement for angle B, which is 53 degrees, okay? All right, let's turn the page and do some of these problems together. For problem number 21, they want us to solve for the cosine of x, which is equal to the square root of 3 over 2. Okay, let me find a spot for my calculator. It's seeable. Okay, first things first. The square root of 3 divided by 2 is equal to a whole bunch of numbers, decimal, right? 0.8660. Yikes. Okay, So now we need the inverse because we want to find the degree measure. So I'm going to take inverse cosine, throw the answer in there, close my parentheses, equal 30 degrees. So letter C. All right. For the next problem, problem number 12. For problem number 12, it says 36 minutes in degrees. Looking at problem number 22, we have 36 minutes and they want you to show your answer in degrees. Well, remember takes 60 minutes to equal 1 degree. So 36 divided by 60 tells me it's 0.6 degrees, okay, which is answer D. All right. For number 23, it says convert 48 degrees, 36 minutes, 12 seconds to the nearest thousandth of a degree. Well, let's try that on our calculator. So to put this on our calculator, you're going to put in 48 and you're going to hit your degree, minute, second button. And then 36, same thing. And it's just going to put up another degree. Don't worry about it. 12, same thing. Then you're going to hit enter. And it's going to say 48 degrees, 36 minutes, 12 seconds. I mean, it's not asking a question, but that's what it's stating. Yes, that is our answer. And then hit this button again, your degree, minute, second button. And it changes it to a decimal version, okay? So 48.6033333, okay, which is letter A. All right. Let's take a look at problem number 27. For problem 27, it says using the following triangle, which of the following expressions would result in the measure of angle A? Well, with the information we have here, we have the opposite over the adjacent, right? Or we have the opposite and the adjacent. So we would use a tangent. To find the actual measure, we would need the inverse tangent of 6/8. So the letter is C. 28, given the following angle, if A equals 2 and B equals 3, find the measure of angle A. Well, this is very similar to the problem we just did up here, right? We want the tangent inverse of 2/3. So let's get our calculator out here. And I'm going to take the tangent inverse of 2 divided by 3. Close my parentheses, equals 33.69 degrees, which we would round up to 34. And so it's letter A. All right? Okay. Go ahead and finish the rest of these problems and then meet me back here for the next part of this section. The last part of section 1 begins on page 18. And again, we're talking about indirect measures. It says you can solve many real-life problems involving measure by applying right-angle trigonometry. The first thing you should do when solving word problems involving trigonometry is to draw a picture of the situation. Normally, I wouldn't probably have read that, but I am a big advocate for drawing a picture of what's happening, okay? So, example here on page 18. A surveyor measures the width of a river indirectly as shown in the diagram, okay? So here's where the surveyor's standing. They're trying to measure this width of this river. She sights a landmark across the river at a 90-degree angle from where she's standing. So here's our 90 degree. There's a landmark right there. When she then measures the angle to the same landmark at a distance of 60 feet. So she went 60 feet over here, okay? She still sees the landmark, but now she measures that this is a 35-degree difference or a 35-degree angle between the side of the river and the landmark, okay? Already she has enough information to solve for how wide this river is. She has an angle measurement and she's looking for a tangent, right? She's looking for an opposite over adjacent because she's got the fact that she walked 60 feet to this new location, all right? Important to draw this because it's what helps you visualize what's actually happening, okay? So she uses the inverse tangent, or sorry, not the inverse tangent, the tangent, and solves for x and learns that the river is 42 feet wide. Okay. And here's a definition that I want to highlight on page 19 here. If an object is higher than the observer's eye, the angle of elevation, of the object is the angle between the horizon and the line of sight object. So the angle of elevation is this, okay? Sometimes they'll just say that, the angle of elevation, the angle of this, okay? But this book seems like they put it in. But if it's a story problem, they're not always going to have the drawing for you, right? So let's take a look at this Chrysler building example. The Chrysler building in New York is 1,046 feet high. How far would you be from the building if you found that the angle of elevation to the top was 75 degrees? So you're standing here, your angle of elevation is 75 degrees. They want to know how far away are you from this building? So again, we're going to be using a tangent because it's opposite over adjacent, except this time we're solving for the adjacent, right? And they've solved and found that for you to have a degree measure, an angle of elevation of 75 degrees, you would have to be 280 feet from the building. Okay? And then it says, make note, the phrase angle of inclination is often used instead of angle of elevation. So those two terms apparently will be used interchangeably. Okay, let's turn the page. The next example at the top of page 20 says on level ground at point A, the angle of elevation, so this angle here, from the top of the tower measures 57 degrees 20 minutes. The distance from point A to the base of the tower is 100 feet. How high is the tower? Okay. Again, they're setting up their equation for tangency, right? We're trying to find this. So it's opposite over adjacent. How high is the tower? Yeah, they used the H here. Sorry, that threw me off for a second since usually we use H for hypotenuse. I had a glitch there for a second. So opposite over adjacent. And then they solve. Tower is 156 feet high. Okay. This is the type of trigonometry that's used all the time. Now, another definition is the angle of depression. Okay. The angle of depression of the object is the angle between the horizon and the line of sight to the object when something is lower than you. Okay. So this example here is this one with a boat. The angle of depression from the top of a boat to the landmark is 30 degrees. Now, remember, it's not going to be this measure because we're talking about from the horizon. Okay, so it's this 30 degrees. If the boat is 25 feet high, how far from the land is it? How far away is it from the land? Well, this angle measurement, while important, isn't part of what we need to work with, right? But they're claiming that this boat, okay, is at a 90-degree angle. So that tells us that this is a perpendicular 90-degree angle as well. These two angles, right? So if this one's 30, then this one must be 60, and then we can solve. Okay? Okay. One more topic here, or one more definition, so to speak. It says the slope or grade of a line is the rise or fall, the vertical distance, divided by the run or the horizontal distance, okay? So the grade of this angle is the rise divided by the run. How far up or down did it go divided by how far to the side, horizontal distance, okay? Vertical over horizontal. So this is a 5% grade or slope. All right, and then they figured out the angle measurement of 2.86 degrees. All right, one last little note here at the top of page 21 is that often they use the symbol that looks like a 0 with a line through it. Not all the way through it though, almost kind of looks like a pill, okay? The symbol is the letter theta from the Greek alphabet, okay? So a lot of times when we're talking about angle measurements we don't know, they'll use the symbol theta. All right, so that's just a note. Let's take a look at number 34. It says the top of an antenna tower is 125 feet above ground level. The tower is to be anchored with a guy wire 20 feet. Okay, so this whole thing right here is 125 feet. The guy wire is 20 feet below its top to the point on the ground, 80 feet from the base. Okay. What is the length of the wire? Well, we can figure that out with, honestly, just using the Pythagorean theorem, right? We don't need to use trigonometry, really. We have the length of this side. We have the length of this side. Not drawn to scale, obviously, but that's fine. Most of these triangles won't be to scale. The numbers will look weird. Just use the numbers that you're given to solve the problem. So we know that 105, the quantity squared, plus 80, the quantity squared, is equal to x squared, right? I don't know what 105 squared is, so let's pull this out. And that is 11,025 plus 80 squared, 6,400. So 6,400 plus 11,025 equals 17,425. We take the square root, closing our parentheses, and we get 132.00 something, so I'm not going to worry about it. So our cable, the guy wire, needs to be 132 feet long, which is answer B. All right, looking at number 35. A 40-foot ladder is used to reach the top of a 24-foot wall. If the ladder extends, so here's my ladder, right? Here's my wall. If the ladder extends, they're really giving you, they're really setting this up for you, right? 10 feet past the top of the wall. Find the measure of the angle that the ladder forms with the horizontal ground, which is right here, angle A. So they want the measure of angle A. We know that the sine of angle A is opposite over hypotenuse, okay? So if the sine of angle A is equal to 24 divided by 30, then angle A is going to be equal to the inverse sine of 24 divided by 30, okay? So grabbing our calculator, we are going to punch in the inverse sine of 24 divided by 30, closing our parentheses, equals. So angle A is going to be equal to 53.1, so we're just going to call it 53 degrees, and that's letter C. Okay, let's turn the page and look at a couple more. Problem number 38. From the top of a cliff 426 feet high, the angle of depression, so remember we're talking about from the top in the horizon, the angle of depression of a ship is observed to be 18.2 degrees. How far out is the ship? All right, well, to solve this, we actually need to solve for one of these, this other angle measurement. Remember, since we are standing here at the top of a cliff, our cliff and our horizon make a 90-degree angle. So if we take 90 minus 18.2, we see that this is 71.8 degrees. And now we can actually solve. This is the angle that we're using, right? 70. So the tangent, opposite over adjacent, the tangent of 71.8 degrees is going to be equal to x over 426. To solve for x, we're going to multiply both sides by 426. And so we end up with 426 times the tangent of 71.8. So I'm going to move, so my calculator could be in here. So the tangent of 71.8, closing my parentheses, times 426 gives me 1,295.6, so 96 feet, which is answer B. All right. Okay, let's do one more and then finish the rest on your own. 139. In the construction of a certain road, a viaduct, a type of bridge, that's what this is, must be built over a railroad track. The viaduct will be 31.5 feet higher than the road level. The rise of the road is to be uniform and is to start a distance of 618 feet from the base of the viaduct. To the nearest degree, what will be the angle of the rise? So they're looking for this. They're looking for this angle measurement. To solve it, we have a tangent. Again, we have the opposite over the adjacent. So the tangent of theta is equal to 31.5 over 618 feet. Now, they want the nearest degree, so we actually need to find theta, which would be the inverse tangent of 31.5 divided by 618. All right, so gearing us up here, we want the inverse tangent of 31.5 divided by 618, closing parentheses, 2.91, so theta is equal to 2.92 degrees, okay? Not a multiple choice, so you should mark your answer. All right, that's the basic setup of this first section of book 3. All right, go ahead and finish these problems, and then when you're ready, meet me back here for section 2. Section 2 begins on page 25. And it's about angles in the coordinate plane. So now we're going to look up, we're talking about angles, we're going to start putting them in a coordinate plane, okay? The following is a list of some Greek letters that may be used to name angles. We have alpha, beta, theta, and phi. I should probably look that up. But an angle is said to be in the standard position when the vertex is at the origin, and the initial side of the angle coincides with the positive part of the x-axis. So this is the initial side of the angle. An angle in a standard position is positive angle if the line generated, or the terminal side, okay? Because remember, an angle has two sides. Here's our initial side. We have it lined up with the x-axis. Its terminal side is rotated clockwise or counterclockwise in this case, so it is a positive angle theta. Now, if this terminal side had been rotated in a clockwise manner, then it would be considered a negative angle. All right, and the picture for this is actually on the next page, which rubs me the wrong way all the time, but let's turn the page and actually look at what they're talking about here. So you can see here that our initial side, is always going to be on the x-axis. When we move up, I guess, in a counterclockwise way, that is a positive angle. And when we move down in a clockwise way, it's going to be a negative angle. It says knowing whether an angle is positive or negative is the first step to determining which quadrant the angle is in. An angle is said to be in a quadrant which the terminal side lies. So this angle here is in the fourth quadrant because that's where its terminal side lies. Remember, quadrant 1, 2, 3, 4. We number them in a counterclockwise way. Angles whose terminal sides coincide with one of the axes are called quadrantal angles. So at 90 degree, 180, 270, 360, those all fall on an axis, so they're kind of in between the quadrants, okay? For this example, it says determine the quadrant which the terminal side of the given angle lies, right? Well, if you have this drawing, this is 1 and this is 2, so it's in quadrant 2. Quadrant 1, 1, 2, 3, 4, quadrant 4, 1, 2, but it's a negative angle, but it's still in quadrant 2, okay? 1, 2, 3, quadrant 3, right? Those are pretty straightforward. Coterminal angles. Here are some examples of angles greater than 360 degrees. Sometimes the angle goes around and then keeps going, okay? But where it stops is always an angle that belonged originally to some other angle, right? It's going to be a coterminal angle because once you pass 360, all the angles are just repeating themselves. So coterminal angles have terminal sides that coincide. Given that one rotation is 360 degrees, you can find coterminal angles by subtracting multiples of 360 from positive angles or adding 360 degree to negative angles. All right. In this box here, it says subtracting multiples of 360 is the same as dividing by 360. If you divide, okay, you'll get a decimal number that indicates the number of complete rotations as well as any fractional part of the rotation. So a 750 degree angle divided by 360 is 2, so it went around 2 full times, and then 0.833. Well, the 0.833 is what was left, right? Is the coterminal angle. So if we take just the decimal and multiply it by 360, we'll see that that's 30 degree coterminal angle, okay? Let's look at these examples here. So determine the quadrant which the terminal side of the given angle lies. 400 degrees, they simply subtracted 360 to show that the coterminal angle is a 40 degree angle, okay, in quadrant 1. 835 degrees, they subtracted 2. Now, this just told us we could divide, so let's take a look at that process. If we have 835 degrees and we divide it by 360, we get 2, so we know it goes around 2 full times, 0.3194444. So if we take 0.319444 and we times that by 360, we see that 114.9 or 115 degrees is what's left, which would put us into quadrant 2. Okay, and so you can do that with all of these, even with these negative ones. Let's look at letter E. For this one, it is a negative 835. It doesn't really matter if you mark it as a negative right now. Just know that negative tells me it's swirling in the other direction, right? And so where my 115 ends up is going to be in a different place. But if we divide that by 360, 2.31 is exactly the same. So 0.319444 times 360 gives me 115 degrees, but it's negative, so we need to move 115 degrees under like this, which puts us in quadrant 3. All right, let's turn the page. Taking a look at problem 2.6, determine the quadrant in which the terminal side of a given angle lies. 230 degrees. Well, I know that is greater than 180, but it's not greater than 270, so it's over here somewhere, which is quadrant 3. Okay, remember, 1, 2, 3, 4. Roman numerals, right? But that's the basis of it. Determine the quadrant which the terminal side of the given angle lies. 115 degrees. Oh, why I drew a circle? Only Jesus knows. Okay, 150 degrees means I'm going this way. More than 90, so I'm going to end up in 2, which is B. All right, let's take a look over here at problem number 18. Choose all of the angles that are coterminal with 150 degrees. 150 degrees. And so what that means is our angle moved in a negative direction to 150 degrees. And so what other angles happen to be right here? Well, since a circle is 360 degrees, we know that if we take 360 and subtract 150, we'll end up with the other side that would end right here, right? Which is 210 degrees. So that's letter D. We know if we add 360 degrees to 210, we get 570 degrees, which is E, right? If we take negative 150 and we add, oh, I just did that, didn't I? 150 negative plus 360 degrees would be negative 510, okay? But it's not going to be either one of these. So it's definitely A, D, and E, okay? Let's see what's left. Oh, that's it. All right, finish the rest of these problems and meet me here for the next part of section 2. So the next part of section 2 is going to lead us into the unit circle, which is probably why I drew a circle on that last problem, but I was getting ahead of myself. The unit circle is a special circle that we use with trigonometry quite a bit, and it tells us that the unit circle is defined as a circle whose radius is 1 and the center is at the origin of a coordinate plane, okay? How this helps us is when we make an angle, we know, and we'll do it up here since it's already done for us. If you envision this on a circle, I'm not sure why they cut it out, but the radius is always 1. So whatever point we choose along this circle, right, our radius or the hypotenuse of our triangle is going to be a 1. Our y value, as much as we go up, right, is considered the sine. And our x value, as much as we go over, is considered our cosine. So remember, the cosine is, here's our theta, adjacent over hypotenuse, so it's x over 1, so it's x. The sine is opposite over hypotenuse, and so it's the y value. It says if a point on the terminal side of an angle, theta, lies on the unit circle, then the xy represents cosine comma sine, which I actually talked about in the last book when they gave us that unit circle with all the different sines and cosines on it, right? Remember I told you that's going to be useful to keep handy? Well, this note would have been useful back then, but here we are now, okay? The tangent, because it's opposite over adjacent, is y over x or sine over cosine, okay? It says here you can reflect the point that is in quadrant 1 as follows. Reflect means, you know, move it around, right? So we're going to follow along here. We can reflect it over the y-axis to the point in quadrant 2 when we make our x value negative. So same values, except this time our x value is negative, okay? We can reflect it through the origin to quadrant 3 when both the x and the y are negative. And we can reflect it over the x-axis to point in quadrant 4 when the y value is negative and the x is still positive, right? And this leads us to some important things. We'll turn the page and take a look. The reference angle is the acute angle formed between the terminal side of an angle and the x-axis. So remember, the reference angle is formed between the x-axis and wherever our terminal side. So if our terminal side is over here, let's say it goes like this, my reference angle has to come back to the x. It's this angle. I mean, it's not the best drawing because I made it pretty small, but we'll talk more about it in a second. It says you can write any angle greater than 90 degrees in terms of its reference angle, okay? The reference angle, this is obviously a most likely 200 something, right? But you would use the reference angle here, which is going to be an acute angle. It says notice that the reference angles of quadrant 2, 3, and 4 can be determined using the following patterns, okay? If the angle is in quadrant 2, you subtract that from 180 degrees. If the angle is in quadrant 3, you subtract 180 degrees from the angle. And if the angle is in quadrant 4, you subtract the angle from 360 degrees. All right? Then there's going to be certain signs involved there, because remember, we were reflecting when we made the x negative or the y negative or both, right? And so that's what this top part of the second column on page 32 talks about. The values of sine and cosine will have the same sign, positive or negative, as the value of the coordinates in the quadrant where the terminal side of the angle lies. Since x is negative in the second and third quadrants, the cosine value is negative there, right? Since y is negative in the third and fourth, sine value is negative there. The tangent becomes negative in the second and fourth quadrants where the x and y coordinates have opposite signs, okay? And this is a little, right here, this coordinate is a little, a mnemonic device, I guess, or something to help you memorize, right? It says down here, to help remembering where the trig functions are positive, start in quadrant 1 and use the saying, all students take calculus. In this quadrant, the sine, cosine, tangent, all positive. In this quadrant, only the sine is positive. In this quadrant, only the tangent is positive. And in this quadrant, only the cosine is positive. Okay? So that's what it means. All students take calculus. All of them are positive. Sine is positive. Tangent's positive. Cosine is positive. All the other parts are negative. So that information alone helps us to identify where angles end up based on the signs of their sine, cosine, tangent. Okay? Looking at this example here. Express cosine of 120 degrees as a function of a positive acute angle. Okay? First, we have to find the reference angle. We're going to take 180 degrees and subtract 120, and we get a 60-degree reference angle. Okay? Because this angle is going to be out here somewhere. This is angle theta, right? But this here is our reference angle. So we take the 180 and subtract this piece to find out that our reference angle is 60 degrees. Okay? So then they've determined that the cosine of 120 degrees isn't the negative sine of 80, it's the negative sine of 60 degrees. They are equal. Cosine of 120 degrees is negative 0.5. The sine of 60 degrees is 0.5, so that's why they have the negative here. Negative sine of 60 degrees is going to be equal. Looking at the next example, express the sine of 280 degrees as a function of a positive acute angle. Okay, well, where is my 280 degrees falling? Right? I mean, you don't really need to know, I suppose, but it is helpful to, for me anyway, to be able to see it, right? 280 is just slightly past this axis, okay? And so this is my reference angle here. So I'm going to take 360 degrees minus the rest to find that it equals 80 degrees. My reference angle is 80 degrees. So the sine of 280 degrees is going to be equal to the negative sine of 80 degrees. Negative because in this quadrant, my sine would be a negative answer. Okay? Got to remember what quadrant we fall into. One more example here. We're going to look at, let's take a look at this one here. Express the sine of 845 degrees as a function of a positive acute angle. Okay. We are going around and around, okay? And then we have to get to 845. Well, it terminates over here somewhere, okay? And so this is our acute angle. This is the angle that we're working with here. So we're going to take 180 degrees minus 125, because that's how much past we went a whole circle, right? And they get 55 degrees. So the sine of 845 is going to equal the sine of 55. Positive both, because sines are positive in that quadrant. Okay? Okay. Let's turn the page. Looking at number 20, in which quadrant is the cosine function positive and the sine function negative? Okay, if you need to turn back and look, where is cosine positive but sine is negative is going to be in quadrant 4, which is letter D. Okay, that's what a lot of these questions are about. Let's take a look here. You don't have to do number 24 if you don't want. That's up to you. Looking at 25 though, which of the following trigonometric expressions is equivalent to the sine of negative 150 degrees? All right. I like to draw, not like all the time, but I mean, I like to draw my math. So here is my angle, right? Here is where my terminal side is. This represents the fact that it's negative. So the distance I have left to go here, right, 180 minus 150 is a 30-degree angle. That's my reference angle, okay? But it says which trigonometric expression is equivalent to this negative sign, okay? Well, in this quadrant, remember, only the tangent is positive. So I know my sine is going to be negative in that area. And the only one that shows me a negative sign is of 30 degrees is part C, or answer C, okay? Excuse me. 26, which of the following expressions is equivalent to the cosine of 125 degrees? Okay, so we're moving over this way. It doesn't matter exactly where, right? But I'm creating my reference angle. I need to take 180 degrees minus 125 degrees, okay? And I get 55 degrees. So this is 55 degrees, my reference angle. Now, it says, which of the following expressions is equivalent to the cosine of 125 degrees? It's going to be the cosine of 55 degrees, but remember, because my cosine is my x value, it's going to be negative over here. So it's going to be negative cosine of 55 degrees, A. Let's do one more of these. Which of the following expressions is equivalent to the tangent of 245 degrees? Now, 245 doesn't quite make it into quadrant 4. It's over here. I usually make that a dotted line, sorry. Here's our reference angle, is this bit right here. So we're going to take 245 and subtract 180 degrees, which is 65 degrees. Okay, so our reference angle is 65 degrees. In this area, my tangent is the only thing positive, so it's going to be letter B. Okay? Go ahead and finish these off, and then I believe we're going to be starting the last part of section 2. The last section here is trigonometric values of special angles. There are a couple special angles that we need to look over, and these are angles with a measure of 30, 45, and 60 degrees. They're considered special angles, and let's take a look at why that is. The 30-60 right angle, we usually call it a 30-60-90. It rolls off the tongue a little bit nicer, I think. Looks like this, right? The short side is opposite the 30 degrees. The long side is opposite the 60, and the hypotenuse is where the hypotenuse goes, opposite the 90-degree angle, okay? And then here are the special measurements that we can determine from that. The hypotenuse is equal to 2 times the short leg. The short leg is equal to half the hypotenuse. Those are just opposites of each other. And the long leg is equal to the short leg times the square root of 3. These are the special measurements that we can get from these type of angles. So if we place a 30-degree angle in the standard position with point P on a unit circle, then the short leg, since our hypotenuse is 1, our short leg is equal to 1/2. Here's our short leg. Our long leg then is going to be equal to 1/2 times the square root of 3, or the square root of 3 over 2. So they found the coordinates for angle, or for point P, at square root of 3 over 2, comma 1/2. Okay? And there's a bunch of other things you can continue to do with that problem. The top of page 37, it says it's important to note that the sine equals 30 degrees, or sorry, the sine of 30 degrees is equal to the cosine of 60 and vice versa. Cosine of 30 is equal to the sine of 60. That's because the sine of an angle is equal to the cosine of its complement. They are called cofunctions. So if the sine of theta is equal to the cosine of 75 degrees, find theta. Well, theta is just the complement, okay, of 75, which is 15 degrees. All right. The next special angle is the isosceles triangle, right triangle, and we usually call these 45, 45, 90s, right? Now, there's only one rule really in the 45, 45, 90. They don't go into it specifically, but the hypotenuse is equal to the side, that's an S, times the square root of 2, okay? So in this one, we know the hypotenuse is 1, So we would have to solve that 1 is equal to the side times the square root of 2, dividing square root of 2 by both sides, which is, I mean, they use the Pythagorean theorem here. We're just doing it slightly different. A side is equal to 1 over the square root of 2. We can't have a square root of 2 in a denominator, so we multiply, and we get that our side is equal to the square root of 2 over 2, which is the same answer that they got. So I would make note, hypotenuse is equal to the side times the square root of 2. Okay? And then in evaluating, they have this nice little chart they put out for you. And it says here, you can fill out the sign of your chart, memorize the signs, it says, and you know how I feel about memorization. Mark what page this is on if you feel so inclined to do so. But honestly, just knowing these shortcuts would be a big help in solving these types of problems, okay? All right, let's turn the page. Example, find the exact value of the sine of 225 degrees. Well, the angle terminates in quadrant 3, and the sine function is negative in quadrant 3, so they take 225, subtract 180. The sine of negative 45 degrees is the square root of 2 over 2 based on that chart, right? But negative, because our sine is negative in that quadrant. So they're using the chart to solve most of these. Find the exact, that's what it means by exact value, right? We're not taking the square root of 2 and rounding. So when they want exact values, most likely your answer is going to have a square root of some kind in it, most likely. So finding the exact value of the tangent of 120 degrees. So remember, 120 degrees is going to end over here somewhere, okay? If we take 180 and subtract 120, we get that this is a 60-degree angle, the long side, right, of a triangle. And the long side is the square root of 3, okay? The hypotenuse is 1, always going to be 1. So that's how they're getting their answers here. So from that chart, they know the tangent of 60 degrees is the square root of 3. Because tangents are negative in this quadrant, they put a negative sign out front, okay? So take advantage of that chart. Again, I'm not asking you to memorize it necessarily, but know where to find it. Okay, let's take a look at some of these problems. Problem number 33. The sine of 210 degrees is equal to what? Well, 210 degrees is going to be over here somewhere, right? And so we take 210 and we subtract 180. And that is going to give us a 30-degree reference angle. Tangents are the only thing positive here. Remember, all students take calculus, so tangent is the only thing positive here. So my sine is going to be negative, and it's going to be answer B. Keep the sign on the outside, or the negative on the outside. The sign of negative 30 is not what you're looking for, okay? So answer B. Let's take a look up here at problem number 35. Find the function value cosine of 150 degrees equals. Well, 150 degrees is going to put us over here somewhere. Okay, there's our reference angle then is a 30-degree reference angle. Okay, we took 180 minus 150 and we got a 30-degree reference angle. In this quadrant, cosines are negative, so we know it's not this or this, okay? So looking at our chart, what is the cosine of 30 degrees? It's the square root of 3 over 2, so our answer is B. All right? So make sure you're using that chart. It's very helpful. You can use it on your tests and your quizzes. Of course, it's always open book, so you can use any of the information in here to help you take those. All right? Go ahead and finish those. That is the end of section 2. I know this is a bit of a longer video. As always, if you have any questions, don't hesitate to contact me. I'm happy to help. Otherwise, until next time.